Okay, now we want to talk about what does motion look like if you're in a moving frame of reference. So first, let's talk about if you are in an airplane and then you had a coin and you flipped it up into the air, and let's first assume the plane is not moving. So if the plane is just sitting there on the tarmac and you flip the coin's going to go up into the air and then it's going to come straight back down into your hand. Okay, same thing here. If I take this thing and I let it go, it falls straight down. Now the first picture there says what's going to happen if you're in a moving frame of reference, so the plane is moving with a constant speed. A constant speed. So if it's moving with a constant speed and you take your coin and you flip it, it's going to go up into the air and come straight back down as though you're at rest. Well, you are at rest. You're at rest with respect to the airplane. Now the airplane is not at rest, so the airplane is moving at a constant speed. But you can't tell that. So if you are in a moving frame of reference that is moving at a constant speed, you can't even tell that you're moving. Now if you look out the window, that's a different story. You can see the ground moving underneath you, and so then you could say, oh, I am moving. But there's no experiment that you could do inside the airplane that would prove that you're moving. So all the laws of physics would be the same in a frame of reference that's moving with a constant speed. Okay, the next thing is, what would happen though if you are in an accelerating frame of reference? So now you're still in the airplane and you're on the runway and the plane is taking off, so that the plane is now accelerating. It's not moving at a constant speed anymore, it's accelerating. So as the plane is accelerating, you flip the coin, and then this time it doesn't go straight up and then come straight back down, but you notice that it goes up and then it goes over your shoulder. Okay, so what's different about this accelerating frame of reference that makes the coin do that? So remember that as long as the penny or the coin is connected to you, it's going at whatever speed you're going at. So as you are accelerating, you flip the coin. Okay? So here's the coin right here. And let's say that the second that you flip it, it has a certain speed, because the airplane has a certain speed as it's going down the runway. Okay, so once this coin has this speed, it will always have that same speed. Okay, so that's Newton's first law of motion. So an object in motion stays in motion with a constant speed. But your speed changes. So let's say that this is at time t equals 0. Okay, and so this would be your speed, and I'm going to make your speed is the same as the speed of the coin. At the end of, let's say, 1 second, so 1 second has gone by, your speed has increased. Okay, but the speed of the coin is the same. So that means that the chair will have moved further than what the coin has. So the chair that you're sitting in has a greater speed than what the coin does. So your chair is going to move further than what the coin does, so therefore the coin is going to be kind of left behind, and it's going to be going over your shoulder. And then at the end of another second, your speed is even greater, but this speed here is still the same. So that as time goes on, that coin gets further and further behind your shoulder. Now, what about the third picture there? So the third picture shows what would happen if you're coming in for a landing. So now you are landing in your airplane, and the second that the airplane begins to slow down, you flip your coin. Well, notice this time that the coin goes in front of you. So why is that true? Okay, so as soon as you flip your coin, the speed of the coin is the same as the speed that you were going at when you flipped it. And so let's say that you're coming in fast. So let's see if I can erase this. Remember that you're coming in fast so that your speed is pretty big. So I will put a large speed here, and then this is the speed of the coin as you are flipping it. So it's the same as your speed the second that you flip it. But let's say 1 second later, you're going slower. So your speed now looks like this, but the coin still has its original speed. So therefore, the coin is going to go in front of you as a result of this. So the point is that in an accelerating frame of reference, you notice that you have what appears to be different laws of physics. But it's just because you're in an accelerating frame of reference. And so this was one of the things that Albert Einstein noticed, was he tried to come up with a coherent way of explaining motion in an accelerating frame of reference versus one that was stationary. And so subsequently he came up with his laws of general relativity as a result of that. And so he found that forces would look different in an accelerating frame of reference, speeds would be different, time would be different, mass would be different, and so he came up with formulas that would connect the two frames of reference, and that's the general theory of relativity, which we'll look at a little bit later in the course. Okay, so just want you to see that in a frame of reference that's moving at a constant speed, the laws of physics will be the same. But if you're in an accelerating frame of reference, then things look kind of weird, but it's just because of your reference frame. All right, let's take a break. And when we come back, we will do our lesson quiz.